In this video, we're going to learn about some of the preparatory concepts for the bioenergetics lecture. The second half of this semester will be spent on metabolism, which is the sum of the chemical reactions carried out by living cells. There are two different types of organisms categorized on how they fuel metabolism, specifically how they find a carbon source. Autotrophs can use CO2 that they breathe as a carbon source, while heterotrophs need carbon from organic molecules like glucose. Which kind of organisms are humans? If your inclination was heterotroph, since we eat food, you're absolutely correct. Ultimately, the components that make up organic molecules are cycling between both autotrophs and heterotrophs with solar energy as the driving force. There are two different types of metabolic pathways, which are connected by the recycling of cofactors and of chemical energy. Catabolic pathways break down nutrients, while steroids build you up, as anabolic steroids are the ones that athletes take to make stronger muscles. At the end of the day, the regulation of these pathways to determine the right molecules are produced or consumed at the right time is key. Regulation is dependent on the availability of the substrate, as will become especially important in the next few chapters, allosteric control, as we've already seen with ATCAs, and growth factors and hormones, which we've hinted at with signaling, but we'll see at the very end of the course. When we learned about the classes of enzymes, I promised you we would see each type of reaction in metabolism. These are just some examples of types of reactions we will see in metabolism. Which classes of enzymes would catalyze each? Hint, hint, this will be part of your pre-assignment to help get you back in the groove for metabolism, where we're going to be learning about several different enzyme reactions. We're going to be learning about individual pathways at any given point in time, but it's important to remember that all of the pathways we'll be learning about, and many that we won't be learning about, are all connected. Within metabolism, you'll see three different types of pathways. We'll see convergent catabolism, where several pathways break down molecules into the same unified molecule. Diverging anabolism, where enzymes act on the same precursor molecule to make a variety of different molecules. And finally, cyclic pathways. One of the reasons we've hammered thermodynamics in at the beginning of the semester, other than the fact that it's important for protein folding, is because it is so important for metabolism. If we review, the Gibbs free energy is the amount of energy that is available to do work. The Gibbs free energy has two components, the enthalpy, or the heat content, and the entropy, or the randomness. During protein folding, we spend a lot of time worrying about the delta H and the delta S, but for now, we're really only concerned about the delta G, because the sign of the delta G tells us in which direction a reaction, and by extension, a metabolic pathway, will proceed. And negative delta G is exergonic, which means the system has energy to do work, while the positive delta G is endergonic, which means that work has to be put into the reaction to make it happen in the forward direction. For a reaction to be spontaneous, or to proceed without any extra input, the delta G must be less than 0. We also previously touched on the idea of the standard state, but just to review, here we go. The delta G naught is the free energy change under standard conditions. This is an inherent characteristic of any chemical reaction at a defined set of parameters. 1 molarity of each chemical, 25 degrees Celsius, and 1 ATM. The naught comes from the addition of the biological, or the prime comes from the addition of the biological standard state conditions. pH 7, 1 millimolar magnesium, and 55.5 molar water. Now, anyone who's performed an experiment with a biological sample knows that working with 1 molar of a protein or nucleic acid is next to impossible. For this reason, we have to correct for the actual concentrations and temperature of the molecules involved and tack that on to the standard state free energy change to get the actual delta G, no naught, no prime. So if we are looking for the free energy of A, and assuming we are not at equilibrium, we have to take the G naught prime, or the standard state free energy of biological conditions, and add it to the gas constant, or R, times the temperature, again, adjusting for a difference in temperature, and the natural log of the concentration. So taking into account any deviation of our molecules from 1 molar that is defined in the standard state. Again, we can think of the second term in this equation as a correction factor for the actual conditions of the reaction. In class, we'll talk about how to quantify the delta G for a reaction and how the delta G is related